I'll introduce myself. I'm Shiva Amiri. I'm Director of Research Infrastructure at 23andMe, and I've been on the review committee for MLconf for a few years now.
Okay, I'll give myself a quick introduction while we're waiting. So hi, everybody. John Maiden. I am the head of machine learning at Cherre, a data tech company in the commercial real estate space. Prior to working at Cherre, I was at JP Chase on the consumer side for about 4 years, trying to deliver insights to millions of Chase customers. Met a long, long time ago, also was in physics, but that's been a long time.
That sounds great. Okay, I think we're good to get started. So great that you already introduced yourself. So you made my job easy. So I don't have to do that, but the floor is yours. So I'll just duck out and then I'll come back in at 1:10 for the next session.
Sounds good.
Over to you. Thanks.
Okay, everybody. So today what I'm going to talk about is lessons learned from building a real-world knowledge graph, all the exciting work we've been doing at Cherre. So as I said before, my name is John Maiden. I work at Cherre, which is a commercial real estate data company. I'll have a slide for the company in a minute. Prior to this, worked at JP Chase on the consumer side, trying to find lots of insights into customer behavior. Contact information, feel free to reach out, ask questions and the like. I'll also have it at the end. So today we're going to talk about the knowledge graph that we built using commercial real estate data at Cherre. So the interesting thing that we did with this is it's a large graph. It's constructed with a lot of messy data. The intent was to build all of this to help drive insights and drive where we wanted to go with the product. So a lot of different talks I've been given about knowledge graphs in industry tend to focus on graphs being structured for queries, so they might have very complex ontologies. We built this with the intent of building models off of this. So the structure of the graph is going to be a little more simple than you might see in some of the talks. But the idea is that we wanted something that could be reused across multiple product directions and could be built using different models. So that's how we focused the work of what we're doing. And by doing that, we ended up using a lot of different ML techniques to first build the graph and then mine information from it. So I'm going to start off with the business use case that drove our work in the first place, very important. From there, finding the right data. You can't have a knowledge graph without really good data. So how we explored what we had and what we needed to find. The graph construction itself, so the nitty-gritty of everything that needed to be built to get it there. So a little bit of machine learning, a little bit of engineering. And then finally, measuring success, which is always important, and that's tied heavily back to our business use case. So quick introduction to Cherre. Cherre is a data connector in the commercial real estate space. What we do is we connect foundation, which is usually the public data sources, paid, so third party like demographic data, payroll data and the like, as well as our customers' own data. We connect it in through a series of pipelines that then deliver the data through APIs that they can use to analyze all of the different data feeds in one place. So while we're doing introductions, I should also give a quick overview of real estate data and explain why it's very messy. So real estate data as a whole is collected in the US at the county level. So there are 3,000 counties in the US. A lot of the regulations, a lot of the conditions and restrictions are based at the state level. So if you look at all of the data sets, they're very wildly different. Texas is a good example of a state with not a lot of reporting requirements. So different states have different reporting requirements. They might have different codes. If you want to get all of the national real estate data, you actually have to go county by county. And the way that real estate works as an industry typically is there are a couple of big providers who that's what they do, is they just go out and on a regular basis have connections that go and collect all of the 3,000 county level data sets that they need and combine it into a national data set that you can use. Cherre doesn't do that. That's not our part of the business, but we use these national providers to then add insights on top of that. These data sets tend to be very ubiquitous in commercial real estate. The types of data that is provided in the public level is going to be the tax owner. So whoever is currently paying taxes on a tax lot. So a tax lot or a tax entity is going to be, could be an apartment building, it could be the building itself, especially if it's a co-op, it could be an empty lot, like whatever is the tax object, that's what people are looking at. That's collected by the assessor's office. The tax owner isn't necessarily the owner of the property. You could have an accountant who files your taxes could be the tax owner, could be listed even though you own the property. It's whoever should get the tax bill. And then on top of that, the deed transactions, which is in the recorder. So deed transactions could be buying and selling activity. It could be transfer of mortgage. It could be transfer of title. Like there's a lot of data in there and it's very complex. I should also just quickly shout out the difference of residential real estate versus commercial real estate. So residential is what most people are familiar with, single family homes, condos, apartment units. It's a B2C type business. There are millions of units, lots of data points. Commercial is multifamily, so you're looking at 4 or more units in a building, so apartment buildings, office, retail, industrial. In terms of this business model, it's more B2B. So, the difference of buying $100,000 for an apartment versus, $1 million for the building. So there are different, different perspectives, different sets of data. I mean, there's a lot of overlap on the public side, but, it's a different set of players. So to build this graph, we have to look at what's our business use case? Why do we want to build a knowledge graph? What do we need to get out of this once we've built and constructed this? So the first initial use case that we used to drive this was finding the true property ownership of a property. So commercial real estate, very commonly, buildings are bought using an LLC on a per property basis. Sometimes this is for tax reasons. Sometimes this is for business structure. Sometimes they just don't want to be found. And so you might see the same company might own 123 Main Street and 124 Main Street, but the two buildings, the owners on tax assessor would be 123 Main Street LLC and 124 Main Street LLC. So they seem like two separate business entities. So what I did is I went and grabbed 2 distinct properties in the US. One of them is in Oceanside. The listed tax assessor owner is Pulte Homes New York LLC. The other one for North Carolina is Luxor Special Purpose Vehicle 1 LLC. If you know the real estate industry, you know Pulte Homes is a developer. Obviously, the actual owner is Pulte Homes, so you can tie that up to the true owner. For Luxor, the actual owner is Amherst Financial. And the way that I did this is I just looked at the mailing address. So in the data, the public data layer, it'll list the tax owner, but it'll also list the address of mailing address. And so you take that, you dump it into Google. Google says, okay, Amherst Financial mailing address, go. So you could say, okay, well, this isn't too tricky. All I'm going to do is I'm just going to take all of the data I have, just take all those addresses and just dump them into Google and see what I get. Might take a little while, but I'll get all of the owners of the property. Well, that doesn't work very well. Reason it doesn't work very well is that there's certain owners who just don't want to be found. Williamsburg, there's a house there that is very popular with a certain part of the community where they just don't want to be found as owners. And so you have a whole bunch of anonymous LLCs that have the same exact address. They are all separate owners. They're all separate businesses. They are just making sure that you can't find out who they are. And so they all use the same property in Williamsburg. So if we actually accomplish this, if we're able to take the data, clean it up well enough, and get it to find the true owner, who's going to use this, right? That's the motivation, is who's our ultimate owner for the user for the data. And that's going to be a couple of different players. So if we can get contact information of the true owner, that's going to be really useful for brokers and developers. They find a property online or they find a property physically. They really like it. It's not listed. The owner's an anonymous LLC. We can say true owner plus phone number and email. They're very happy. They can call and they can cold call to make a deal. If I then say this property is owned by a Tishman Speyer, I can then flip it and say, okay, I got Tishman Speyer as the owner. Tell me all of the other properties that Tishman Speyer owns so I can make this a portfolio level analysis. Given that this is a temporal graph, because we've got decades of real estate data we can use, we can slice and dice and say, what is someone's history over time? What are they buying and selling? There are other support network information that gets into here. So you get who are the lenders, usually on the part of the mortgage information. Maybe they're using a certain property manager that you might get from the data. So if you want to break into that market, you want to go into that neighborhood, here are the lenders that have a history there. Here's a property manager that's got history. The other really useful part is that you can use this to then start building property comps. So residential real estate, if I find a house I want to sell, I say, what are 3 or 4 other houses that are close to my house that have the same numbers of bedrooms and bathrooms? And they sold for X in the past 6 months, so average of that is value of my house. That works in residential because there's a lot of properties and it's easy to find something nearby that you can sell. Commercial real estate's a little harder because most buildings are bespoke, and you're not going to find an apartment building or a industrial center that looks exactly like yours that's close enough, that's sold with enough time. So you have to think about more data sets and more ways to give insight to the data to then build out evaluation models. So we know what we want to do. We want to be able to find honest owners. We need to find the data. So on the data side, this is a nice generic commercial real estate picture. They're looking out into the distance. They see all the opportunities. They know they want it all. Okay, let's attach real data to this. So on the real data side, we have transaction data. So we know building was sold on a certain date for a certain amount. We might know who the mortgage lender is if we know that was, the mortgage was attached to the transaction. Given that most of this is tax related, so that you'll know what the assessed taxes are. Maybe you care about abatements and the like. So, and also certain places might provide a market value, so you'll get an estimated market value. You get some assessed taxes on a property. If we have permit data, then if you're logging a permit, you have to list a person and a contact. So the person who's connected might be useful. Depending on the permit information, it might be someone who's connected to the owner, or it might be someone who's just a general contractor. And then you also get a whole bunch of different government listed properties. So that's what we got to start on finding the data. Now, on the general requirements of what we want. Oops. So finding the data, so general requirements. Overall, what we know we need is first, who is the taxpayer behind this? We get that no matter what. We get the transaction history as well. That's part of the public data layer that we want. Permits data requires a little bit more looking, but if we get that, that's useful because we have contact information. We've got people who are definitely connected to owners. Those are things we can dump into the graph. No matter what, public data is also really important. So the top developers all have a listing of all of their properties. So if they have big properties, they're very proud of them, they're going to list them on their webpage. If they list them, our customers can find them. We also have to have those same answers. So we need to know the properties that Tishman, Vornado, CBRE, all the big names have, and we've got to make sure that we incorporate that into our graph. And then landmark information is also really useful. So anyone can look up who owns the Empire State Building on Wikipedia. We make sure that we have to have the same answer as well. So no matter what, the obvious answers also have to be incorporated into the graph. To be able to do all of these connections, we need to know about corporations and the registration. So corporate structure is also very important. If I see a subsidiary, can I tie it back to the parent? If I see a random mailing address, not everything that they're going to list is their corporate headquarters. So can I get enough mailing addresses that tie me back to different parts of the same company? Contact information, also really relevant for our customers. So we also have to capture that as a separate data pool. And then lots of anonymous LLCs, is particularly if you register everything in Delaware. So can we get as much LLC registration information as we can to then also join that back into the overall graph? So we've got our goal, we've got our data. For anyone who is interested in trying to look at real estate data themselves, I recommend looking at New York City data sources. So New York City has a great open data initiative. Most of the great data is provided by the Department of Finance. So tax data is in AV Roll. The transaction data is in Acris. It's been there, lots of history, lots of years of data. Buildings also has some great insights on New York City buildings as a whole. So if you're interested in giving it a try and seeing what real estate data is available, New York City's got a lot of great source data, and they also put a lot of effort into creating primary keys that allow you to connect all these different sets together without too much effort. I should also add that we did this, originally we did this as a prototype with New York City data, and then eventually we redid it all using national data. So we have this, we have our data, we have a goal. Let's talk about the actual graph construction. So, as you know, building a knowledge graph, you want to focus on what is considered to be the most important parts of your data. So nodes are the highlight of your graph. In our case, a property is going to be a big focus, or in this case, it's really a tax lot. Addresses that we capture from the data are also going to be important. So when I say address, usually it's going to be a mailing address because that's going to be associated to the owner themselves. Property addresses might be relevant, but you can assume, especially on the commercial side, that property addresses and mailing addresses are going to be two different things. And then from the names that we collect, we want to distinguish between people names and originally what we called non-people names, but really just generally corporations. This is going to play into how we mine the graph and what we look at. So, assigning different relevances and weights to whether the connection's a person or not has an importance on how we decide ownership on the property itself. And then from a corporation, we care about if it's registered versus unknown. So we need that database of registered company information. For our use cases, for our customers, they care about, is a property owned by a government entity? Is it something maybe owned by an education institution? So we need to provide additional filtering and tagging based on the companies themselves. And then the edges are the source. So different sources are going to have different weights and different values. If we're looking at some type of a transaction, I want to know which side of the transaction you're on. So I'm going to put that into the edge weight information. And then recency and frequency as well. So that's the basics of the graph. Like I said, this is not generally for overall querying. It was designed for modeling, so it doesn't have a very deep or very complex ontological structure. From an engineering perspective, we take all of the different data sources that we're pulling in. So a lot of the sources already mentioned. We clean and standardize names. We clean and standardize addresses. I'll talk about why that's important. And then we put it into the knowledge graph as a series of edges. So for the purposes of what we're doing, it really is an undirected graph. It doesn't really matter if a property connects to an address or address connects to a property. For the technologies we're using, particularly we're using Spark graph frames. In that case, it really expects a directed graph. So just making sure that we were building it out, that we made sure that we kept our data was consistent, and we made sure that our graph was directed in the right way. But otherwise, yeah, large graph required big data tools. So what did we do with this? So we take the data, we pull it out, we build some edges, and we try to mine it for owners. What we do is we just say there are a couple of different motifs, and we're not looking for extremely complicated ones. We had about half a dozen motifs that we looked at total. And we were saying property connects to this and property connects to that. If okay, that's our first one. And then we did this as a waterfall approach. So we said, if I see this pattern first, I know this is the most relevant pattern that I care about. And if you match that, you're good. This property is put aside. And so what we were able to do is we were to reduce the space of our connections over time. So the graph actually shrunk, and we iteratively went through each one of the patterns to make it smaller and smaller. Basically, the stages that we had were the most confident, and that got the largest chunk of the data. And then we would reduce it more and more until we got to the connections that were more and more tenuous, but by pulling out a lot of the old data. So we pulled out as much as we can. It made the graph run a bit faster at the later stages, but it also made sure that some of the data points that might have been less relevant were also removed from the graph, so that it really kept to stuff that was more that we cared about for this. But generally, like I said, we looked at specific motifs. We then looked at the data sources, and we ranked them based on what we consider to be relevant or not. This graph in itself is built at scale. So there are about a couple of hundred nodes in the graph, a couple of 100 million nodes, 1.5 billion-ish edges to the graph. So there's engineering challenges, which goes back to having to run this all in BigQuery and Spark. So making sure that we could build this, and the assumption is, even though the graph is large, what could we further compress so that we could add more data sources without making it even larger? So keeping it at a relative size that could be run in a couple of hours using Spark. But then on top of that, there's also the analysis challenge, because it is so large, we're not going to be able to immediately point and say, we know that we got all this right. There is no way to check all of these points and determine exactly if we got the right answer. So analysis becomes very important, and this ties into the metrics that I'm going to talk about at the end. So on the machine learning side, the graph itself, building it, there are a whole bunch of different interesting challenges. They're primarily NLP based. So on the address side, addresses can be very noisy. Some of them are they're different ways to write stuff. We're a Manhattan-based company. We used to be on 6th Avenue. So 989, 6th Avenue, and Avenue of the Americas are all the same thing. You need to be able to take those, standardize those, and come up with one canonical form of addresses. In addition to that, you also might have typos. So most of the address might be right, but you get the state wrong or the zip wrong. Maybe you fat fingered a little bit. So on that side, what we had to do is we had to build a point of speech tagger for address components. There are a couple of different packages out there. We built something from scratch, but there's a lot of analysis on how to take addresses, which are short semi-structured text, and basically tag them for street number, street name, and everything else. For those that are interested, there's stuff. There have been papers and projects around conditional random fields for point of speech tagging on this. I've seen hidden Markov models. I know someone out there put a deep learning model together for tagging addresses as well. So there's a couple of different ways, but it is, it's short semi-structured text. All you've got is the address. That's it. And you want to make sure you can parse the address quickly. You can identify the tags and then join it against a large database of clean addresses that you can use. So you need a good set of clean address data to begin with, and then you can component-wise fuzzy match it. This becomes a bit more of an engineering challenge, but then it allows you to try to clean up the addresses as much as possible to come up with one form that can then be that node that you put into the graph. That's at least a little bit more straightforward because with addresses, you have a gold standard of data to work with. On the name side, that becomes a bit more tricky because names are a lot bigger. There's a lot, we had hundreds of millions of names that we saw. Names could be people, they could be companies, they could be trusts, they could be government entities, they could be a whole bunch of things. And so first of all, we wanted to type them. So the first way that we did it was people versus non-people. John King has to be a person, Burger King has to be a company. We started off with some obvious keywords and then did an iterative approach. So LLC, corporation, trust, all of these things were potentially words that we could build into tagging. And then you could iteratively find other similar words and then build upon that to tag a larger and larger data set. And what we found is that we had hundreds of millions of names. There were certain names at the tail end that were very obvious. So if you see LLC in a name, it's obviously a corporation. You can put it onto one tail end of your work. There's certain names that you might see. If you see a name, I don't know, Stephen, Karen, David, something like that, potentially it's going to be a person that would be on the other end of the spectrum. And then you'd have a whole bunch of names that would fall in the middle that would be kind of ambiguous. So you start off just creating a data set that was large enough that covered everything, figured out where you had the really strong signals from the end. And just, you could do a simple lift score based on, the names that you've collected, but you say collect the tail ends. And then what we eventually had to move to was for all the stuff in the middle, we actually did build a model. So we trained a model off of the labels that we had created with the assumption that the labels were mostly good. Addresses are short semi-structured text. Names are not structured at all. And people names versus non-people names have different formats and challenges. So we used out-of-the-box simple text embedding. So character level text embedding for all of the strings, dumped that into a model as well as a couple of other insights that we had on features, and then predicted at scale over a couple of 100 million names, people versus non-people. Once we did the predictions on the types, then we had to go ahead and do further cleaning. So the example I have here is Grant Harriman, Schwartz and Klinger, which is actually a law firm. So you might have different forms of the same name, and you want to be able to standardize those. So you might have, John Maiden LLC and John Maiden LLP. Those are probably going to be the same company. You want to make sure that you can cut down on the noise, because if you have one, if you have one name one version of a company name that points to one address and another version of a company name that points to a different address, you want to take those two names, consolidate them together so that you know that this is really the same underlying company and it points to two different addresses, which then gives you insights to further connect, because otherwise the graph itself is just going to be too noisy and you're not going to have the insights and connections that you need. So for some of this, regex patterns work really well. People names, there isn't much to do because there's just so much variation in people names. At least company names are a little more behaved. Typo correction at scale and graph-based feedback loop, I'll quickly talk about that. So the typos, there were lots of typos that were in the data. Remember that this is all collected at the county level, which means that people are just typing it in by hand. There's no consistent pattern at all. And so, we could quickly whip up a typo correction. So we had millions of names. We extracted out the most common names. We then did some hashing to avoid n-squared comparisons because we had hundreds of thousands of words that we wanted to look at. So LSH to get some of the words in the right bucket. We were just looking for simple typos, so things that were at least one character away, because we actually wanted to go in and manually verify that the typos were typos. And so, a simple typo correction would be hashing to reduce the space, Levenstein of 1, just to make sure that you get something close enough. And then on top of that, we just had a dictionary, so to make sure that, hotels and motels didn't get mixed in together. So that's on the typo correction, which is an iterative process that you run. The other way that we also did it was using the graph to clean the graph. So taking the data, cleaning it up as well enough as we could, and then using the connections that we had to then try to further imply additional connections in entity resolution. So if we knew that 2 different John Maidens connected to the same property, we could then say, obviously, John A. Maiden and John B. Maiden are 2 different people. Let's keep them as distinct entities. But if we have 2 different big name corps that both point to the same address, we could use that, string similarity, business rules, you take your pick. All of those would then say, nope, these are actually the same entity. We need to collapse them together into one single node. So then it actually becomes an iterative feedback loop where you take the data, you clean it as well as you can, you use it to build the graph, and then you use the graph to then go back and come up with new lists of consolidation, and that'll help collapse the graph even further. So that's on the graph side. The last piece of the puzzle is measuring success. So to be able to do this, we have 150 million properties total, more than. How do we actually determine what's the way to measure success? Because there's no way we can verify all of these results being correctly. So this is where domain knowledge really goes into it. We care about certain asset types. We care about certain owners. For the most part, a lot of properties in the database across the US are going to be single-family homes. Those are owned by people. We expect that our patterns and our motifs are going to capture those very easily. So if those get captured, those are pretty good. And we should say, most of the, a large chunk of the data up front is going to be good enough to be able to use. What we care about is the last 10, 15, 20%, which is the commercial real estate space. And that's where we need to put our time and effort into analyzing and making sure we get it right, because that's what our customers are going to be looking for. So we're going to focus on, potentially we care more about multifamily compared to retail, or office compared to industrial. We're going to have to narrow it down to a certain asset type that we care about, because we're going to have to go in and manually check some of this, at least some of the samples. And also on the owner side, the big names everybody knows about, they're not that interested in. It's the middle space on real estate where they care about owners who have, more than 1 building, less than 500. Can we focus on those and get those right? And additionally, we just had, finding gold standard data sets, because we have little bits of one set that might cover one geographic region for one asset type, another will cover a different region for a different asset type, and trying to use those to then triangulate what success is going to be. But no matter what, prioritizing continuous improvement is important, because we are constantly having to improve. We're getting new data sets. The data constantly updates. We find, there are places where we want to improve. Maybe we want better contact information. Maybe we find a certain region the data isn't sufficient. And so being able to put in place ways that we're constantly measuring the success of our results. So that's the talk. Are there any questions I might answer?
Any questions for John? That was great. Thank you very much, John. There's a question from Dan.
Yep. Maximum number of edges. So 1 billion, 1.5 billion so far in the setup. So yeah, that's about, it's not a huge graph, but it's definitely large, and it's not something that would fit in a single computer. Okay. Oh, ontology. Yeah. Okay. So how would I deal with updating data, particularly changes in structure ontology and other changes in the data set, and is that stable? Okay. So in terms of ontology, the general structure is, like I said, we've kept it pretty simple because we want to use it for a couple of different approaches. So, we only have a certain limited number of data sets. We only have a certain limited, very generic types of nodes. And so, we are constantly updating the data. We get new tax data continually. We get new transaction records. it's more about the infrastructure, making sure that can update and run on a regular basis than the actual ontologies, because those are pretty, like I said, they're kept to a certain setup.
That's great.
Yeah.
Thank you very much, John. That was excellent. Really appreciate that. Very clear and engaging.